what we'll talk about a little bit is take a little bit of a macro view of how machine learning has evolved over the last 30 years, and then what does it mean for us engineers sitting here, right? So, do you have a clicker? So we'll begin by sort of quickly going through some of the key AI moments where, in some sense, some form of AI beat human at some task, right? And I think I'll probably come to why I'm touching upon them, right? Some of us might remember the Deep Blue, IBM Deep Blue movement. I think Piyush and I were in school then, where people were trying to teach computers to play chess, and suddenly you had a mechanism which was very brute force based, beating Kasparov, the world champion then. Or you all know about AlexNet. We had a presentation talking about image processing as well, where until, let's say, ImageNets came up, AlexNet came up, people used to do image understanding through feature detection. They would write feature detection codes in software, and suddenly you had a mechanism which detected these features through some structural priors. Transformers you all know about. I think Go, again, AlphaGo was another sort of interesting moment in AI history where AI, which learned to self-play and played over millions of games, beat heuristics written by humans, right? So even as recently as DeepSeek. And I think I want to quote this beautiful essay by Richard Sutton. Richard Sutton is also somebody who is considered as father for reinforcement learning, which drives a lot of ML innovation, which is that I think we as humans sometimes overrate ourselves. We as computer scientists and engineers overrate ourselves, right? The biggest lesson that we have learned is what has worked and scaled very well with AI is when you look for mechanisms in AI which scale with computing and data. We try to hard-code our heuristics the way we think in software. What really works is let computers figure that out, let software figure that out, right, with some constraints. I highly recommend reading that essay if you haven't, right? Now, just another stepping back here, right? So we all know about classical AI, right? When I was in grad school, I remember a neural network lecture in a machine learning or an AI course with the disclaimer that we'll probably never use it in our lifetime, right? So there's classical AI, which was essentially you're trying to solve a problem. AI is about solving a problem, right? About building software that can solve a problem the way a human would, or possibly better, right? Classical AI was trying to search for a solution in a solution space, right? Machine learning was about learning to find a solution, or learning the software learning a solution to a problem from data patterns and experience, right? And I want to stay with these two keywords here, search and learning. All AI that we do now comes down to these two keywords. And I said neural networks was one form of machine learning. Now, this chart is interesting. How many of you have heard of Kaplan's scaling laws? Some, yeah. So there were, before neural networks became what they are now, there were other forms of machine learning being used, right? Or other forms of AI, classical AI being used. We'll talk about some of them later. But what this chart illustrated is, here is a way of, here is a form of AI which actually gets better the more data and compute you throw at it, right? So on the x-axis is, so the different lines here indicate the amount of compute that you have used to train that model. The y-axis is the loss on a specific task. And the x-axis is the size of the model. So the more you go in the yellow region, it means the models are bigger. You've used more compute. And for higher compute with a larger model, you get actually cutting down your loss. And this was something which other forms of classical AI or machine learning didn't have. If you marry that with the fact that computing has been scaling, we almost can expect it to grow in some shape and form, in different forms, possibly. I think that was moment that made a lot of people bet on neural networks, including the team that I'm part of, right? I think I work with the Turing team at Microsoft. The Turing team's foundational thesis is that neural networks have a capacity to scale. Let's invest into that early, back in early, mid-2016, 17, 18 era. We did the first few large foundational models, TNLG, TULG series of models, some benchmark suites as well. I think many of these models were state of the art. This is before some of the GPT-5 recent models. Now we own the Copilot. We do a lot of frontier pushing work within the Copilot space. The introduction was a little flattery. I wouldn't claim to sort of lead ML team in India, but a lot of frontier pushing work is done by our team. Now, so the other things I'll talk about is coming from our experience over the last few years building such systems, right? So while I talk about the general trends, all of these are grounded in real trial, error, experimentation, as any sort of experiential learning should be, right? So classical machine learning, we talked about search whether you're trying to solve a problem by searching in all possible spaces, which is a decision tree kind of a mechanism, or you're trying to learn a function which approximates what you want to get, right? If you're trying to sort of take a combination of variables and infer some value out of it and you don't know what the weights would be, that's a function parameter search problem, right? It worked to a certain extent. Then came modern machine learning, where you had different structures or architectures, CNNs included, transformers included, and these were the models learning the weights with some structural constraints. The reason why CNNs work for a while is because in their structure, they allowed learning the weights which have the translational features to be there, locational features to be detected. If you had to do it the entire thing as a completely dense network, it would be many more features and the models wouldn't have learned. So the space that we live in or the work in is so fast moving that if I talk about something from 3, 4, 5 years ago, it still looks pretty old. So let's say a couple of years ago, people started looking at how they can make LLMs better, right? So you learned from data, and there are different mechanisms. By definition, machine learning is learning from data, but there are different mechanisms you could learn, right? Those are also the areas that you could do something like supervised fine-tuning, which is you have humans annotate answers to question, right? Or scoring. So the space is overall heading towards how do you sort of free up the human constraints, whether it's in data generation, to be able to do better models, right? So supervised fine-tuning was one mechanism, but there you needed good quality human judging on the data. To preference modeling, which was then used in reward models, but there it's easier to judge 2 data points and say this is better than that, as opposed to sort of scoring each of them to a certain more discrete scale. To more recent sort of how do you let these LLMs or these large models reason at the time of the question being asked, right? So talking about search and reasoning, search and learning, this is about searching at the time of answering the question, right? So we have all heard of chain of thought probably when you work with LLMs, and I'll probably switch between general AI and LLMs a little more interchangeably. Tree of thought we have heard of, right? So another pattern I earlier referred to, things that mimic what humans do, how we learn, seems to have generally scaled well. Now, if you ask me a question, do I utter the first thing that comes to my mind? Probably not. I'll probably think through one path and say, nah, this is not the correct thing. Maybe I'll think through another path and then say, this looks correct, if you ask me to solve a problem, right? So we are not, our response to a question is not a single linear inference run of our LLM, that is our brain, or model, that's our brain. We do multiple reasoning paths, backtrack, come back to another reasoning paths, right? So borrowing that inspiration, people brought in different mechanisms to use these models, say LLMs, to solve different problems. Can I pursue one path? At every stage, verify, are we heading towards the answer? If not, backtrack, pursue another path. Imagine it's not a single chain of thought, but I'm sort of pursuing different trees there, right? And easily it was found to do better on, let's say, combinatorial reasoning tasks, even fuzzy tasks like writing or puzzle solving. The models seem to do well. Yeah. Extend that analogy. Instead of a single tree, you could have multiple trees, and do the same thing as well. So we were, all of the while we were talking about how does AI learn from human annotated data. But you can imagine we are at this point where we may reach, for a lot of the problems that we want AI to solve, we don't have enough human annotated data. We don't have human, either it's expensive to get that data, we may not have as many sort of trained people to solve, let's say, complex maths problems or research problems. And we've all been looking at how to use synthetic data to extend what we can learn from. I'm good. Thank you. Thank you. Right, so the challenge, in principle, synthetic data looks like a good path. If you could generate data, if I have a problem, I could have AI generate the data, then I'm no longer as dependent on humans for doing it. The problem is, how do you, if I have to learn from myself, I may plateau off, right? If the same model has to generate data and then learn from it, it will reach its own sort of limits there, right? And there are mechanisms that industry adopts now, which were, let's say, in research a year ago, but very commonplace, where you could have AI generate different data through different kind of a tree of thought or chain of thought kind of mechanisms, and score each of them, and select which ones make sense. So if I'm asked to solve, let's say, a complex, go back to our high school days. If you're asked to solve a problem that you're not sure about, you try one approach, compare it to the answer, doesn't work, you try another approach and say, isme answer aa gaya, this might be the right path, and then you say this is, and then you go back and learn from that, right? This kind of problem, I need to take that approach. Learning from AI can do that. AI can probably explore, these language models can explore these different chains of thought, verify at every stage or at some stage, and say this looks correct because it's a verifiable answer, and then put that in the training set for further learning, right? And these are different ways of scoring. I talked about, you could say I explored this path, but you have a rule to say, this value in this solving this problem can't be negative. You abandon that path. Or you could have another LLM verify what the first LLM is doing. And that's very, very common now. You could have one generate the possible solution or generate the next step, another to verify and critique and say, no, this is incorrect for that reason, and then use that to re-explore that path or abandon that path. The specific aspect that I talked about, which is a lot of the problems that we deal with, that we have LLMs solve, have this this very nuanced property, which is that they have a generator-verifier gap. Solving those problems are hard, but if you have a solution, verifying them is easy. And that lends itself beautifully to a lot of generation, right? So this is, again, like the high school problem-solving example, right? You could try 5 different possible solutions, match, you can verify it because you can compare the answer, right? If I have an equation to be solved, solving it may be hard. But once I have an answer, I can put the values back and verify whether it's correct or not. Or if I have to ask, there's a long piece of text and I'm asked specific fact from the text, identifying where the text is hard, but once I know I can, and I know that this part of the text has it or this part of the file has it, it's easy for me to go back and verify that, right? So a lot of the newer approaches use something known as generator-verifier gap, which is you start rolling out these different paths of exploration and prune the exploration when you know the verification check has failed. And papers talking about how these things have led to, let's say, 8x reduction in data that you need to explore, or 8x reduction in the rollouts that you need to expose to be able to train equivalent quality models here. Right? So the larger trend, I still want to call this out. This is still very similar to what we as humans do, not very different. If you're trying some approach to solve a problem, you'll say, this doesn't make sense because it's missed the boundary condition already, right? Search and learning, right? The common theme there. The approaches I talked about, why does it allow you to generate better data than the foundational LLM or the base LLM could be? Because now an LLM is not responsible for the same, even if the LLM by itself has a 20% probability of solving the problem, by doing this, you got that one solution. And then if you use that as a teacher data to train another model, you can actually push the boundary up more than the base model, right? So, yeah. We have all used the O3 reasoning models, probably. The reasoning models, I think we have seen that prevalence come up, right? What I talk about is a mechanism that's commonly used for task-specific learning now, which is the berry rollout kind of a process, right? What I mentioned, explore a solution path, prune it through a mix of verification or other mechanisms. If it solves the problem, use that as a training data and loop back, right? And it works. I talked about it in the context of text, but it works very well whether you're training LLMs to do, let's say, computer usage task, or image understanding task, or video understanding task, right? So it's a space that has sort of worked, approach that seems to be scaling quite well. I'll come back to Mr. Sutton. Another article by him, more recent. He talks about this is called the Welcome to the Era of Experience, right? And the idea here is this. We're talking of a world where, until recently, we were setting the gold standard data for machine learning and AI to learn from. We are getting to a point where AI by itself, through the approaches that we talked about, could interact with the rest of the world, get some experience or feedback, score it through the mechanisms we talked about, and itself train itself from the data. So there is no human in the loop in that sense, right? And that is immensely more powerful. That's the era of experience that we're getting in. We don't need, for all of the very rollouts that we talk about, there's hardly a human in the loop there. You could have mechanisms to verify what model generates its own training data earlier. Now, I come from a very deterministic systems background until a few years ago. And one of the things that people like me and probably many others had to sort of get used to is how we have to reorient ourselves, right? I'll talk about it later as well. So we are all used to a world where you would, on the left side of this simple, you have two dimensions here. One is what kind of problems we have software solutions for, and the y-axis is the quality or precision of solutions. Typically, in the past, we wrote software which were traditional engineering-based, solved one problem to almost 100% accuracy, very narrow problem. We have now neural network-based systems which are far more generalizable than we ever imagined. But the problem is they're stochastic, which means they won't have the same quality precision. They won't be as deterministic. But they are easier to deploy, train, because unlike getting experts to codify the rules, all I need is data, and the data might already be there, and I'm good to go. And some of us would have questioned whether the right side would have worked or not, but clearly they are, right? I think all the technology developments are heading towards taking this right side, and then systems is block higher up as well, towards better quality, precision, performance. So that's a trend that's very inevitable. And what does it mean for software that we write, right? So many of us are engineers here, I imagine, right? We're all, on the left side, we have the classic MVC stack, right? UI, or view, logic, or controller, and the storage and transactions, which are models. I think we're getting to a different kind of a stack at a very high level now. I've seen systems, classic AI native systems, probably will still have a storage, transactions underneath. But would we have a classic view? A SaaS of tomorrow need not have, a lot of what we built in SaaS is imagining the user journeys. A SaaS of tomorrow need not be that. It just could be an agent interacting with me or my agent, deciding when to show what information. Maybe even my queries could be more natural language agentic. And all it does is takes a conversational input, interacts with the storage layer, decides the logic, interacts with the storage layers, and then maybe presents the data back in the way that I want, right? So I may want data in a certain language, in a certain, some parts of the data. Somebody else, Gaurav, may want data in a different language, in a different format, right? So we're talking of a stack which is going to be very different. We're already seeing that already, right? So and these agents could be interacting. You have the agent-to-agent protocol. You have APIs and MCPs there. What's a bigger change, and harder for me also to get used to, is that even within the control plane, instead of I used to take pride in thinking through that. But a lot of the newer AI systems, you have the model LLMs deciding what to do when. When do you keep reasoning and when do you stop reasoning and answer back to the user, right? And that, in some sense, is an ego sort of battle I had to fight with myself when I started working on these systems as well, right? So, how does engineering change? Model orchestrators as opposed to algorithms we talked about. If you work in this space, you will start talking about things like TPIT, TPOT, TTFT. I don't know whether you've heard of these terms, time to first token, because you're now dealing a lot with GPU infrastructure and not the classic MTR and other metrics that you will talk about. All your CI/CD will have some MLOps tool in place. You would look at observability will have a strong ML component. Classically, they didn't. What you ship, what you release, is not going through a classic A/B testing, but it often goes through experimental platform. We all know about the Static acquisition recently. So these are things that as engineers, until a few years ago, many of us may not have played around with, but that's changing for us. Sorry. Can I go back? There was one more slide, I think. OK, maybe. I'll just come back. Yeah, and I think one of my realization, which I'm still sort of learning, is, you know, in good old engineering, we talked about building a good software. We said begin with a unit test. Now, when you build an AI-native application, I think somebody showed the benchmarks for their Glance AI product. Begin with the evaluation set. Make sure you have some form of evaluation harness there. Else, you'll be doing a wild goose chase while you're training the models, because you can't look inside these models. QI, you got to have some mechanisms for judging the results of the model, set of people there. And I think the biggest change, I think, is, as engineers, we like to solve the problem conceptually and maybe build it. A personal learning is spend a lot of time with data. Be willing to spend time with the data through the trenches, see what's happening, extract meaningful insights, because that's a DNA. An applied science DNA is something that, if you have to work with, you can't just take these models by stochastic nature, put them there, and hope it works. It doesn't, right? So, but yeah, so we are seeing some of these foundational elements of the new stack come up. They will probably keep evolving, and I think I don't see the pace of the innovation coming. If anything, these models will continue to solve more problems, more applied, more systems will become AI native, and I think we just have to adapt ourselves to ride that wave.